Okay, I'm Charlie Bertucci, part of the advisory committee along with Nicole that helps put on this conference. Nicole's going to be talking on passive house and the grid while energy efficiency still matters. She's a licensed architect and certified passive house consultant with 15 years experience. She basically has built a building science group within her previous architecture firm, and now she has her own architecture and consulting firm, continuing to advance critical components of building science and sustainability into the future. So, Nicole.
Thanks, Charlie. Thanks, everybody, for being here. I'm excited to talk with you all today. So you know a little bit about what I do. I'd like to take a minute to get to know a little bit about what you all do. So in the room, how many architects do we have? Awesome. How about engineers? Cool. Sustainability consultants? Building owners and developers? No, okay. Builders, contractors? Oh, welcome. All right. Students, yeah. Great. Welcome. So I'm going to talk today about why we should still be focusing on energy efficiency in our buildings. So there's there we go. Okay. It was working a minute ago. There we go. Perfect. Thank you. So a lot of the conversation has been around getting to net zero energy in buildings, and this factors a lot into performance and financial performance on projects, and it's a huge goal that has really been a huge push to get to. So as in the past, it's always been approached as we want to start by reducing the load and then make up the remaining energy use with PV. And a lot of this was because that was how the cost benefit weighed out. PV was expensive enough that it made sense to do the efficiency upgrades first and then supplement with the PV and fill with the PV at the end. As PV is getting more and more affordable, more and more attainable for all these different project types, that balance has shifted. So now in buildings, particularly larger buildings where space is not an issue, the question comes up, why should I bother updating my envelope if I can just add PV and still get to net zero? To answer that question, we need to understand more about the grid and how the grid works and how that factors into project performance, building performance, occupancy, and costs for building owners. So to generalize, the way the grid works, the way the grid was designed to work, power comes in from the generation side. So you have power plants, these could be fossil fuel power plants, they can be wind farms, solar farms, hydro facilities, nuclear power plants. Is grid scale generation feeding in. Then there's the distribution, the transmission aspect, which is a big part of the conversation as we're talking about electrification and how the grid is changing. Not something I'm going to focus on in this particular presentation. It could probably be a presentation all on its own. There are things happening there that could change things in the future. We're going to focus on how it is kind of right now and where that's going. And then at the other end, power goes out. So you have the distribution to the end user, that's commercial buildings, single family homes, multifamily residential, all of the building stock, and charging electric vehicles as that's becoming more and more mainstream. So if we look to start out, take a look at the generation side, and we look at particularly in New York State. So this information is coming from the New York Independent System Operator, which is an independent planning and regulating agency. So they deal with looking at and predicting the overall demand on the grid. What is the capacity of the grid, making sure that there are enough generating resources to meet the estimated and predicted demand that's coming, that there's enough added factors built in so that there's reliability, that electricity is going to get where it needs to go when it needs to get there. And they also deal with wholesale electricity markets. So setting that general starting price of electricity, which we'll get into in a minute. So on this slide, we're looking at New York State's electric grid and where does electricity come from for us in New York State. Now you'll see on here, there's a portion that's coming from fossil fuels and a very large portion coming from renewables, which is great. In New York State, we actually have a couple of different things going on. So the majority of the fossil fuel use is coming from downstate. Upstate is very renewable. It's mostly renewables. There could be a whole nother conversation about upstate versus downstate that ties into that transmission. For this presentation, we're going to focus on looking at New York State as a whole. So here we're looking at renewables at grid scale. So this is the large scale wind farms and solar farms and hydropower feeding into the grid. We also have renewables at building scale, right? They're called distributed energy resources. Any building that has solar panels on the roof, for example, it makes enough energy to cover the building's own needs, but also feeds back into the grid. So now we have energy coming in from one side, going out on the other side, and energy coming back in from that side. So this causes some additional complexity to the grid because now the grid has to manage and balance this energy coming in from both directions and make sure that it's still covering the demand that's required when the demand is required over time. So what that looks like, when you look at load profiles, it's a balancing challenge. So you have renewable generation. This happens on a daily basis, hour by hour over the course of a day, in that the majority of the solar production is happening when the sun is shining up in the highest point of the sky in the middle of the day. So in the middle of the day, there's overgeneration. So there's more energy feeding back into the grid when people aren't using it. And then earlier and later, when there's not so much solar production, but there's more demand on the grid, there's no solar to make it up. So there's under generation causing peak supply issues that the grid has to make up for. On a seasonal basis, we see something a little similar. It looks reversed. So there's under generation in certain points of the year when there's high levels of usage. And then again, there's over generation in those shoulder months when there's not as much usage, but there's still a lot of generation happening. So when we look at this as net zero and we say, okay, we're using energy sometimes and we're generating energy other times, and we say, okay, well, I'm making more energy now, so I'm going to give that to the grid and they're going to hold on to it for me. And then when I need it later, I'm just going to take it back. But the grid is not a battery. That's not how it works. They still have to manage. There's more energy coming in than energy going out. And what are they going to do with that? It's not the grid scale battery storage is not a thing yet. We're not there. Current battery storage, speaking of battery storage, is time limited. So you can put energy in and it depletes over time. So it can help in short time period durations, maybe on that hour by hour daily case. but it isn't helping much with the seasonal changes. It's also at its current state in a cost prohibitive point. Certain building projects can afford to incorporate some battery storage. On a grid level, putting in enough batteries is still cost prohibitive, and it's space prohibitive as well. So looking to the future for those battery technologies, but we don't know when they're coming or if they're coming. So looking back, the other point to make about renewables is that they're intermittent. So you can't turn on the sun when you need power to supply to folks who are demanding it. So the grid needs generator sources that can ramp up quickly and provide power when suddenly it's ramping up and everyone needs to use it. So those peak providing generator types, renewables not really compatible with that. It's called dispatchable. So because these are intermittent and they can't be ramped up quickly, they're not considered dispatchable. Moving into the future, we're going to need research and development to come up with zero emission dispatchable resources. We don't have them yet. So speaking a bit about peak versus baseload generators. So again, this is from the New York ISO. It's a nice chart to distill down what are the different generator types, what fuel are they using, how are they distributed, and what are they used for. So from this, you can start to see where renewables and clean energy resources can be used for the base load, the kind of flat demand over time that's always going to be there, but can't be ramped up quickly enough to deal with those ramp ups or used for the peak. So for those types of load scenarios, we end up going to fossil fuels. So here we're talking oil and natural gas, and again, depending on where you are in the state. Digesting this a little bit, you can start to see that reducing the peak usage is directly going to impact fossil fuel usage. So if the peak demand is can only be served right now by fossil fuel resources, and we want to reduce carbon, reduce fossil fuels use, then we should be focused on reducing our peak energy usage. That also ties into pricing. So the way that the New York ISO sets electricity prices, they take the expected electricity demand and they start to fill it up based on lowest to highest cost. So they take the lowest cost generator type, use that to fill as much as they can. Then they go to the next highest cost, and on until they've satisfied the peak demand. And the electricity pricing then is set based on the last type of generator that needs to be used to fill that whole demand. So in New York State, that ends up being natural gas. So suddenly we're looking at electricity prices alongside natural gas prices, and you can see how connected that they are. Decoupling that is going to take a lot of things, but some of it can be dealt with by dealing with that peak usage again. So let's flip over and talk about demand and look at the demand side of this grid setup. What it looks like now. This is in the New York control area, New York State. Our current average summer day, average winter day load on the grid. This also takes into account an estimate of some behind the meter solar. So building PV and what impact that has on reducing the energy use at what points of the day, at what seasons does it happen more or less. So you can see there is an impact there of the solar. So this is not to say that putting solar on the building is not helping the situation. It definitely is. It's reducing that summer peak a little bit. It's also shifting the actual peak in the summertime to later in the day. In the wintertime, we get a little bit of benefit in the middle of the day, but we still have that high peak in the evening. And we'll look at that more specifically in a minute. So right now you can see the summer usage is higher than the winter. So where we are, we have summer peaking, highest energy use. Demand is changing. So electrification is coming. As we know, we've been talking about this for 2 days now. I think we've got it that between the CLCPA and it's just where we need to go. We're going to be electrifying buildings at a fast pace. We need to move. We need to do it now. And it's critical for where we need to go. That said, there are implications of doing that, and we need to be conscious of what those implications are and make sure that we're addressing the challenges that are coming with it. What the New York ISO thinks that looks like is our electricity usage right now. We're probably looking closer to this high load scenario with the amount of electrification that needs to happen. And the things that we've heard across the past 2 days, we know there's a lot of work to be done there. And that's going to make a significant impact on the grid, on electricity, the cost of electricity, and how we're implementing that in our buildings and projects. Along with an overall load increase, we're also going to see a shift, a flip. So the solid lines are where we are now, and the dashed lines are projected as we get into this electrification, what's going to happen. So a lot of electrification is happening on building heating systems. That's changing the winter electricity usage hugely. So suddenly we're going from, we use more energy in the summer to we're using more electricity, to we're using more electricity overall because we've electrified all these buildings. And now we're using more electricity in the winter. We switch from a summer peaking scenario to a winter peaking scenario. That's can be a big deal for what we do with our buildings. There are things that we can do to directly address that. As far as the time frame for that shift, we can look at how that change is going to happen, when that change might take place. So the estimates have the switch. So the dark line is the summer usage and the light line is the winter usage. And you can see winter surpasses summer in the 2030s, mid 2030s. We're going to see that happening. So if we zoom in to central New York, where we're standing at this moment, this is the grid load profile from almost 2 days last week. So the vertical dash lines are at noon and midnight, give a time scale. It's easier to see than the time scale at the bottom. And I've overlaid the green gradient to show generally the availability of solar. So if you were integrating solar into your building, that's when you would get your solar production, most of it. So we can see that we have two distinct peaks per day. There's one happening in the morning, I think it's around 8 o'clock. And then there's another even bigger peak happening in the evening around 7 p.m. There's also a huge ramp up in the morning from the low of the night before. And that's as significant an issue as the peaks themselves. We can also see that the solar production is not necessarily helping with the load profile as we see it. The times are not, it's not happening at the right time. They don't line up. So what does that mean for dollars and cents for building owners? I am definitely oversimplifying this for the sake of the duration of the presentation, but 3 basic rate structures for utilities. So there are others, but for the focus of this, these are the important ones to think about. So there's the flat rate structure, which is primarily residential customers and small commercial customers. And they're paying for delivery charges and for supply charges, a flat rate per kilowatt, regardless of what time of day they're using it. Then there's the demand charge. And I'm simplifying this again. This is for larger commercial and institutional building owners typically. And the pricing is based on the amount of energy that they use during a peak usage time. And this is highly variable. So this can be the peak usage time for the particular customer. So what time does that building use the most energy? It can be the peak usage time for the system overall. It could also be predetermined, where they say, okay, these are the times where you're going to be paying more money, which is helpful to know. It can also be variable. So depending on when you're actually using more energy is when you pay more for your energy. So the demand charge can get huge. I've worked on projects, one with a school district where the demand charge factored in so hugely. They were looking at net zero and passive house primarily to deal with the demand charge issues that they were having. It was like 30 to 50% of what they were paying. It was insane. And then there's time of use. And this is generally commercial and institutional. In New York State at National Grid, residential can also opt into this. So there's an opportunity there. This is a lower cost per kilowatt hour for both delivery and supply charges when for electricity that's used not during the predefined system peak time. Higher cost during the predefined system peak time. It's a more straightforward way to look at it. So if we look at that on a graph, these are made up numbers to show the general relationship of how these rate structures work. Flat rate, green line across the middle there, kind of the middle. And then time of use, which is you paying higher at the peak. It goes down as you get closer to off peak, the lowest at off peak, and then goes back up again. And I'll show you a chart on an hour by hour how that changes. And then demand charge is a big question mark in the middle because it just depends on how the structure is set up and what your usage is. And it can be a really big concern, a really big number. So looking at those charts, this is from National Grid time of use rates based on the time per day. So we have delivery charges on this side, which are based on peak or off peak, and then the supply charges, which are based on the actual time that the energy is used. So here I've highlighted the two peak, the highest pricing points over the course of the day. It's higher in the evening. We saw that peak was higher in the evening. We'll see that in a second. So 8 a.m. and 7 p.m. at time of use, you're paying the most for your electric supply. And back to our graph, you can see that on the dark dashed lines, that lines up in the morning with the increase to the peak and directly with the middle of the peak in the afternoon, which makes sense. Use less during your peak, reduce your peak usage, save money. Another major factor in this that's related to the grid, but different, is resilience. So on the left is a kind of a boring chart from the reasons for the energy generator outages in Texas during the Texas freeze. And it's taken from a federal report. And in that same federal report, it talks more specifically about the results of those outages. And 210 people lost their lives because of these outages and things that could have been prevented. And the descriptions in that report are tragic and so saddening. Stuff that doesn't have to happen. And then on the right side is a map from the New York Times showing the heat waves in California that also took many lives. These are extreme weather events that are becoming more and more common, and they're putting huge strains on the grid. And these are things we need to think about, that we can think about, that we can deal with, and we should be addressing. So overall, I'm talking about a theme. Peak usage, particularly in the wintertime, means more money and more fossil fuels. So what about passive house? How many folks are familiar with passive house? Oh, good. Lots of folks. Great. So the concept of passive house is about reducing overall energy use, but the primary thing to focus on is that there's a specific requirement for reducing the energy used for heating and cooling, which as we're starting to electrify and we're talking about winter peaking, being able to reduce the amount of energy that you're using for heating is going to be huge. The idea is to focus on the envelope. So we're talking about air tightness, an extremely airtight building envelope is critical. Then continuous insulation and right sizing the insulation, and that's going to depend on your climate if you're using the FIA standard. As part of that insulating value, you're looking at your fenestration components as well, your whole building envelope components and how they work together. You want to make sure you've got heat recovery in your ventilation. So that is again helping with reducing that heating load and the amount of energy used there. And then you can minimize your mechanical systems. So as we're shifting all these buildings to heat pumps for heating, we want to make sure that we're not adding to that problem of that winter peak. So what does this look like in a building load? I took this from Lisa White from FIAS. She did the modeling. This is a passive house building. So the blue line is the building load in the winter and in the summer. And the yellow line is the PV production. And I look at the building load in a passive house, and it's so flat. I just want to lay on it. It's so flat. I can take a nap. I mean, that can address so much of what we've been talking about and the issues that are coming. So you're reducing energy, you're reducing peak energy, you're lowering the load. You're also reducing the amount of PV, which PV is cheaper, is not necessarily about spending less on PV, but does factor into less exporting to the grid. So we start to resolve those grid scale issues of balancing and managing that surplus. less importing, less exporting. So to look at this kind of hypothetically, if you remember the time of use charges chart, and we're paying $73 at 7 o'clock and about $40 off peak. And this is a gross simplification again, but it's just to give a framework to look at. And these are, again, kind of made up numbers, but it's a relative comparison. Take a baseline building, use nice round numbers, 100 for peak usage, 60 for off-peak usage. Take a building B, you make the peak usage 50% better. You're flattening it out, so you're not just taking your whole energy use and shifting it down. There's a relative scale going on there. So off-peak usage is not quite 50% better, but it's better. And how that translates, just use the 73 and the 40. You're talking about cutting your cost for peak in half, which can be huge on a time of use scale. So that could be a point where, as a residential customer, you could say, how does this balance out if I'm switching and opting into a time of use rate structure? Can I save money by doing this? And that needs to start factoring into the cost benefit analysis. So ultimately, this is good for you, the building owners and the people paying those bills, because those winter peaks are just going to get more and more expensive as it gets more and more drastic. So being able to use smaller electric heat pumps and have less usage at higher costs through the time of use benefit, or when we're talking about demand charges, can be a huge component and a huge factor in that decision making. We're also talking about resilience. So a passive house level building where you've got air tightness and insulation such that the building can maintain thermal comfort for days. And you think back, I think back to the Texas example again, and there were power outages for days, and the issues of hypothermia and people trying to heat their homes with fireplaces and causing structure fires. If they had passive houses that could maintain safe levels of thermal comfort over the course of those outages, it would have been very different. Safety, resilience, health, strength. This is also good for the grid. So there's less surplus dumping into the grid when there's no demand for it. The grid has less management. There's less peak usage, especially as that gets to be a bigger and bigger component as we're moving to electrification. So there's less strain on the grid, especially in extreme weather events, as climate change and resilience becomes much more critical to moving forward. It also means reduced fossil fuel use. My fossil fuel power plant got really small and gray there. This means we have a stronger and more resilient grid that can serve us when we need it and how we need it. Questions?
Thanks, Nicole. That was great. I love the chart that shows the peak where winter is intersecting with summer and like 20, 30 to 32.
Yeah.
Have you seen electric vehicle charging added to that to see when we might also be tipping all the new EVs?
Yeah, that is another aspect. I didn't have it in here, but yeah. Oh, sorry. It was the chart with the shift from summer to winter peaking, and is there have I seen similar similar data with electric vehicle charging and that ramping up as electric vehicle production and more and more infrastructure for electric vehicles, that's where we have to go. So that's where we're going, and that's going to be a huge impact to that strain as well. Michelle.
You mentioned that could protect against like the extreme temperatures during the Texas freeze, and I just wondered, because it's calibrated to the climate location and the
good point.
Not set for the same kind of temperatures here, is it still effective?
What I think it gets to even more. So when I look at passive house and I say, okay, what's variable and what's fixed. So the insulation values are variable, but the air tightness is fixed. And the thermal control, like if I have clients coming to me and saying, should I insulate my building? And I say, that's the wrong place to start. Is your building airtight? Because before you do anything, you should air seal your building, because that's where you're going to see the most thermal impact actually. So I think, yes, it's a good thing to think about, especially with FIAS where it's targeted to location. Is there a conversation there about how do those targets need to change based on the changing climate potentially? And I think they are starting to do that with using future weather data in their modeling that's coming. But it's a start with the air tightness at least. Good question. Jim.
Curious about all that data. Getting my head around the changes now to the future. So it's about electricity.
Yeah.
Right. The electrical demand is going to shift. So it's going to be more intensive in the summertime.
In the wintertime.
In the wintertime, because we won't need summertime.
The summertime is, we use electricity to cool in the summer already.
Yeah.
So that's not really going, it's going to go up because it always goes up, but it's not really going to be a huge change. The big change is going to be the winter as we're electrifying heating systems for buildings, which use a lot of systems are using natural gas, propane, oil, whatever fossil fuels, rather than electricity for heating.
So your assumption in the future is that's going to change. We're not going to burn fossil fuels for heating anymore.
Right.
Thank you. I just wanted to.
Yes.
And
We're not going to burn fossil fuels for heating anymore. I have to repeat that because that's a really good thing to say.
And in the summertime, we have a lot of air conditioning, of course.
Mhm.
And is it true? Is it true that there's a lot of air conditioning that happens because we don't have very good thermal envelopes? So
part of it.
We maybe reduce the amount of air conditioning in the future if we have more passive house buildings.
That's certainly part of it. There is, so passive house, the FIAS standard does limit heating and cooling. So there is a separate cooling limit as well as part of that. So absolutely.
I mean, do we see less air conditioning in passive houses than normal houses because of the tight envelope?
Mhm. Yep. And the passive house design, as part of it, you also need to look at overheating. So setting apart from like back in the day, passive solar, where you just put south windows on everything, you have to look space by space. Are there areas where you are taking advantage of solar gain when you need it in the winter, and how do you mitigate that in the summer when you don't want it? So you don't have to overcool a space because you've overheated it trying to get some winter gain.
Can you also speak to the fact that passive house requires the efficient domestic hot water and pipe insulation, so you don't have to cool more because of the heat coming off the pipes?
In the space, absolutely. There's so many interconnected aspects to this, and the previous presentation on the sand and CO2 heat pump hot water system and all of the lessons learned, I thought was a really great one to see, to tie into this, the electrification But yeah, the limitations on pipe runs and the requirements for insulating are definitely a benefit. Anybody else?
I would add ventilation to that to reduce the internal heatings or to get rid of them. So, I think that's another, besides, the added insulation.
You mean the recovery?
Yeah, the
Yep.
energy recovery ventilation in the summer. and
Definitely.
Summer bypass to get rid of excess heat.
Yep.
To purposes to reducing cooling load.
Definitely.
Do you have a sense of, fortunately, I'm thinking especially of the places where people live, apartments and family houses. In those peak demands for electricity during the day, do you have a sense of how much of that is driven by comfort, heating and air conditioning, and how much of that is driven by lighting and electronics? Those kinds of
I don't have any direct data for that. But I'm gonna throw out there, and I'm sure there are many folks in the audience who can correct me if my gut instinct is wrong here, that a significant portion of it comes from the comfort space conditioning.
I would guess that, but
Aspects.
I wonder about.
Yeah, is there anybody here who has specific data they could share on? Oh, Brendan. Right. Right. That's got water. For the other folks here, that was Brendan from the previous presentation, saying that it is significant portion does come from the domestic hot water usage as well. You see those peaks in the morning and the evening when folks are taking showers and getting ready to head off for the day, whether they're going to work or working in their living room, and then coming home and doing laundry, washing dishes, things like that. Definitely contributes to that. Pasquale.
I just wanted to confirm that that data on peak demands are averages.
Yes.
Right? So have you done any research on the impacts of actual peaks? In other words, for extreme weather events that have occurred in Texas was not
No.
anywhere near their average.
True.
Peak. It was I think like a very out of the ordinary event, but nonetheless, as the grid is built and maintained and grown,
Right.
we need to accommodate extreme conditions.
Right. Right. Yeah. The question was that the data shown in the load profiles is average data. So has there been any investigation into specific peaks during particular periods of time? For example, the Texas freeze scenario, what did the load profile look like on that at that particular time? Because it would be very different from the average. And that's a good question. Other than the chart, the graph of the central New York usage on a particular day, that was 2 days last week. That's the only specific data that I pulled at this point, but that would be really interesting to look at.
Because that certainly would inform the type of equipment to understand the vulnerabilities.
Sure.
About what actually, peaks happen under extreme conditions.
Right. That future forecasting, I think, is going to be a huge, particularly what do those extremes look like Michelle was talking about with the FIA standard for Texas doesn't really take into account that kind of extreme potential event currently. We have one.
Going back to your CNY graph, is the difference between the ramp up you saw in the first day overnight was is that a function of the weekday versus weekend? Why was the overnight demand so much higher than it was
Get this to go back.
the initial ramp up is huge, but then you have an overnight where it doesn't. Isn't that?
Oh, yeah, that's a good question. So
That's weather related or what if that's a weekend function or?
I mean, this was the middle of the week. last week, the 24th, 25th, I think was during the week. Was it? Now I have to look at the calendar.
That's Friday, 24th is Friday.
Oh, okay, so interesting. Yeah, I don't know. People stay up late on Saturday. I don't know. That's a good question. They all need to go to sleep. I don't know. But yeah, that's interesting that the 2 a.m. Thursday versus 2 a.m. I guess 2 a.m. Friday morning versus 2 a.m. Saturday morning is quite a bit different here.
That our cold snap last
Yeah,
Was it?
weekend?
yeah.
Picked a good time.
Crazy, like, pick up.
Oh, yeah, so that yeah, the difference in the exterior temperature.
Cause I keep my house on one temperature and that day I noticed that it was working more than normal. I'm like, what's going on? And I look at, oh, we have the historical storm.
So that was a particularly cold and snowy day, so that could be why there was more usage overnight, because it was cold and
Yeah.
houses were trying to keep up. Brendan.
That's one of the, that heat pump do a pretty significant, especially our that make heat pumps when it gets cold, that requires lower electrical equipment.
Yep. Yeah, that impacts electricity usage from heat pumps is more significant when it's colder. So that could be factored in as well.
This is more of a comment, and just a reflection, like this is a really important issue. It's an issue that I think about all the time. And when I'm working on project teams and actual projects, I find it challenging to bring this issue and get the teams to understand it and to evaluate it. So we often do we're doing energy modeling, we're doing energy cost evaluation, but we're typically looking at kilowatt hours and not demand. And Brendan just pointed out another important thing. So when you look at the kWh usage and you're comparing, oh, should we go to we're improving the thermal envelope by X amount. When we look at the annual kWh usage, the difference is not that great, especially when you're heating with a heat pump with a COP of 2.5. But when you look at those peak times and that COP derates to 1.3 or 1.4, that extra insulation or the extra air sealing actually makes a really big difference on the grid.
Right.
This is the presentation I want to show my clients. You can't sit them down and
No,
show them
it's hard, right?
But it's a super important issue that is hard to financially sell right now.
Yeah.
And I wish the utilities would buy into this, because this is really going to help them.
Right.
They should be paying for that 5% passive house cost.
Right.
Because they're going to see the benefit in 10, 15 years.
Right. That's a conversation.
So
that needs to
following
be
up
had.
on that idea, so, one of the things I was thinking about is we pay a lot of attention to energy, but we don't pay attention to demand, right? It's just, we talk about energy and the numbers. We pay a lot of attention to EUI. Many years ago, I heard an interesting proposal, which was, the rating, you can model energy and you can tell people what the buildings are used. The rating system should be based simply on how small an auxiliary heating system you're willing to put in your building per square foot.
Which is I think that's kind of what the passive house.
Which
thing
is
about.
just demanded, right? But it takes it one step further, which is, you're telling me you have a model of the passive house, right? I'm not interested in your model. I'm not interested in verifying your model. I'm simply interested, let's get right to performance, right? And just talk about how small can you make it as a design, right? Throw it into the lab. And I think that then creates a conversation where it's very easy to go out to the utility, right? Don't worry about passive house. This is what we're going to do for this building, and this is how we're going to verify it, right? With a single metric, like EUI, single metric there. And so I'd love to hear your thoughts on just, how simple can we make the message, and how direct can we make the performance that we're looking for in buildings?
Right. And I think it's crucial to make it, I mean, in order to be able to communicate it, it has to be clear and simple for folks to buy into it. And there's a lot of stuff going on that makes it more complicated. So I think finding a way to get to that simplification is going to be critical for how we get there.
Like Henry Gifford and Chris Benedict's, yeah, their little energy code presentation.
Yeah.
Passive house, saving money.
Yeah. Yeah, right.
It's easy.
Yeah, you can distill it and then illustrating it
Don't
is
make
going to
sure
be
that money that we take.
the.
Gotta get some good advertising for it. Start hitting the market advertising, making an app. Getting the kids involved, playing video games, about how you save energy in your house. I don't know, let's try to brainstorm on how to get to the new generations involved. Cause I'm pretty sure they're gonna find a way to make it fun.
So I think looking at those specific instances, looking at what are the impacts of those peak demand times. If it were easier to get information from utilities, that would be nice. Took a lot of time to get the limited information that I could pull together for this. And it just, I'm like spinning my wheels and thinking, why is this so hard to figure out? So making that more achievable, approachable. Yeah, go ahead.
If I could just put out a shout out that if there are any students in the room, then particularly
Any
interested
students in the room?
in this issue of demand and data, I'd be interested to talk with you at the end of the session.
We have lots of students in the room, as we saw at the beginning, so great. All right, we're kind of early, but I'm hungry, so that's okay. Does anybody have any other questions? Oh, okay, thank you.